Excellent. Then in prognostic factors, this is where we are now interested in an individual factor. It could be a patient characteristic, it could be a disease characteristic that starts to take that overall cohort and divides it into smaller groups. It could be a binary group, it could be an ordinal group. And in these patients, we're now trying to understand the risk of the outcome more specifically in these individual groups. Or in essence, we're trying to understand the direction and the magnitude of an association between a patient characteristic or a disease characteristic and the risk of a patient-reported outcome. So an example of this would be, maybe I'm interested in the association between the age of a donor and their risk of losing a kidney transplant 1 year after the kidney transplant. So the donor maybe was older, and the older donors compared to the younger donors puts the transplant recipient at a higher risk of losing the kidney graft after transplant as opposed to those who had younger donors. So now if you compare these two, here it was pretty broad in overall prognosis, but now with the second one, with prognostic factors, we're getting a little bit more specific. And finally, when we're talking about accuracy of prediction models, this is where we're trying to understand what is the best estimate of how well a model differentiates between high and low risk patients, and how well a model's predicted risk matches to what was actually observed in the patients, which is a concept called calibration. And an example of this would be, for example, looking at discriminatory and calibration of RECODE, which is a prediction model that's meant to predict all-cause mortality in patients who have type 2 diabetes. So far clear on the different types of questions and the differences in the prognosis streams? Excellent. Now, they do serve different importances. The importance of overall prognosis is that it can be the optimal source of baseline risk in therapy questions. Usually in therapy systematic reviews, what we meta-analyze are the relative risks, intervention A versus intervention B, and we pool that across studies. At the point of developing guidelines, the guidelines don't typically work with relative risk. The guidelines like to understand what the absolute risk is. And the guidelines really would like to know what is the best estimate of that baseline risk to which we're applying the relative effective intervention. So that's where we may want to do a systematic review of overall prognosis. The observational evidence can be very strong in this sense because they can follow patients for different time points for a longer follow-up period, and they can be very informative to that relative risk. So this is an example from guidelines on transcatheter aortic valve replacement as compared to a surgical approach for replacing the aortic valve of the heart. And the relative risk or the hazard ratio for transcatheter aortic valve replacement versus surgical approach, that came from a systematic review comparing the two interventions. But this one box here, which is the baseline risk in the surgical group, that came from a systematic review of overall prognosis studies. So the other benefit of overall prognosis, and I alluded to this a little bit, as you know, RCTs typically they go up to 2 years, maybe 5 years at max. There are some outcomes that we care about that we need to follow patients for a very long time. RCTs can't help with these, and so overall prognosis can give a sense as to what is the risk of an outcome in the very long term. For prognostic factors have two streams of importance. One is that they can be extremely helpful in our future studies. So if we do a systematic review of prognostic factors and we want to evaluate all prognostic factors in a cohort of interest, or a population of interest, I should say, that helps us to identify the factors that matter the most, the ones that actually change the risk of patients. And we may want to use them in future planning of randomized controlled trials, where prior to randomization, you might stratify based on the prognostic factor so that we ensure that that prognostic factor is accounted for and balanced in our randomized controlled trial. The other thing that we can do is, in the absence of having accurate, reliable risk prediction models, right? Risk prediction models that take multiple different prognostic factors and put them together. You as a physician or a healthcare provider will go on your phone, put in your patient characteristics and get a risk estimate. Sometimes we don't have that. And sometimes we still want to get very specific in the shared decision-making process that we have with our patients. What is your true risk? Well, that's where prognostic factors can help and substitute for the lack of evidence on prediction models, right? So if I'm taking care of a patient who's in front of me, I know that she's maybe a woman as compared to a man, and maybe she has hypertension, diabetes. Maybe I don't have a prediction model that puts all of these together, but I have a systematic review of prognostic factors. And from that systematic review, I can tell my patient, well, because you're a woman and you have hypertension and you have diabetes, your risk is expected to be this much higher as somebody who might be a man who doesn't have hypertension, who doesn't have diabetes. So it can start to help us a little bit in clinical decision making. And in the accuracy of prediction models, this is one of my favorite areas, and this is where we're focusing a lot of efforts in GRADE at the moment. In one disease area, like for example, diabetes, type 2 diabetes, you could be presented with many, many different prediction models that are out there. And in fact, that's what we saw. So we did a systematic review of every single prediction model that's ever been done in the area of type 2 diabetes. And when a model's discrimination was evaluated by more than 2 studies, we did a meta-analysis of the discrimination statistics, and that allowed us to, in a sense, have a between study form of comparison across these studies, right? So for a given outcome, which in this case was mortality, and well, you can see all the different outcomes are listed. We had all-cause mortality, CV mortality. Each of these lines was a meta-analysis of its own. And we found that one of the best performing models in type 2 diabetes was RECODE, which then we recommended to a panel of experts who were trying to make risk stratified recommendations for patients with type 2 diabetes in terms of them using SGLT2 inhibitors.
You say this is the one meta-analysis for like a scale or like a prediction model, right?
Yes.
Why are they different? Why do you have to?
Yes. So in therapy, and we're going to talk a little bit more about the differences as we move forward. You would do a meta-analysis for one single intervention compared to a comparator for one single outcome. So your meta-analysis is outcome specific. In meta-analyses of the performance of prediction models, your meta-analysis is specific to the prediction model, and it's specific to the outcome that's being evaluated by the prediction model. So in this case, we had, I don't remember exactly how many patients, but for example, RECODE, sorry, I don't remember how many studies, but we had a bunch of studies looking at RECODE, and the total number of patients in all those studies was 14,247. And this one line, and the point estimate here, 0.75, 0.7 to 0.8, that's the pooled discrimination of RECODE for all-cause mortality. Yeah, is that perfect? I should mention that one thing that's, yeah, of course.
There's a question from Dr. Munoz. He wants to know what estimates the ES in the graph.
Excellent question. This is discrimination. So this would be discrimination, and for binary outcomes, is the same like either area under the curve or concordance statistics.
And what does it stand for?
This is just the effect size. So in a software like Stata, if you don't modify the output necessarily, Stata would automatically say ES, which is an acronym for effect size. Oh, my pleasure. One thing that I'll mention is that, so we do these systematic reviews to get at the validity or the accuracy of prediction models and how well they can differentiate between high and low risk patients, or how accurately they can predict the risk of our patients. But these performance metrics of models are surrogates for patient-reported outcomes. That's a very key important thing that we're grappling right now with as we're making recommendations around the use of models. We can't just stop at a model has an excellent area under the curve of 0.8 or 0.9 or getting closer and closer. Are you familiar with area under the curve? Statistics, yes, excellent. The reason is because there are many different reasons that you may have an excellent model that makes no impact on patient outcomes. Maybe your model is great at estimating prognosis, but we don't have any intervention to modify that prognosis. So in the end, if you implement that model, you're not moving the needle, you're not changing anything about the rest of the outcomes of the patients. Maybe the physicians are not comfortable with the model, and even though the model is wonderful, it's too cumbersome, it will never get used in practice. So there's no difference between an arm of patients who get randomized with the use of model and the arm of patients who don't get randomized with the use of model. So in a sense, that's why we say these performance metrics are a surrogate. We like to believe that the better the performance of a model, the better the impact on patient-reported outcomes. But truly, the only way that we can do that is with a randomized controlled trial where we randomize half of the healthcare systems to use the model and the other half not to have access to the model. Yeah. Excellent. So I thought it would be helpful for us to, before I move on, any questions? Any comments? No, thanks. It would be helpful for us to do a comparison of how prognosis systematic reviews differ from therapy systematic reviews. And I thought this would be helpful to do it this way. Is there a way to make this more forward? And got it. Perfect. To the side. So we have different stages of doing a systematic review, right? So we first come up with our research question, then we decide on our eligibility criteria. We partner with an information specialist to do our search strategy. Then we do our screening for the eligible articles. We do our data extraction to find relevant information on the participants, the outcomes that we want to meta-analyze. And then finally, we do our data extraction. Now, as we talked about, there are differences between the research questions that we ask in prognosis. Okay, it's very specific to whether you're operating an overall prognosis, prognostic factor, or prediction models. Your search strategy is potentially going to be different, has to be different, and I'll show you some of the key things that we put into our search strategies for prognosis. The process of doing our screening is no different than what we do in therapy. The process in terms of minimizing human error, doing it in duplicate, none of that is anything new. The only thing that I would say is when you're screening titles and abstracts, it's very easy for you to get a sense if the question is a therapy question, if it's an RCT or not. In fact, it's so easy that they've developed artificial intelligence algorithms that can do it. Right, you throw thousands of citations in there, and robot analysts, there are tools like this, can separate out which are the RCTs, which are not the RCTs. So there's key features that are very distinct from randomized control trials and non-randomized control trials. In prognosis, things are not so clear always. What happens is, we may end up with a lot of full text to screen, because the abstract wasn't clear. The reason is because the population might be of interest. Maybe it is the patients who have type 2 diabetes. But maybe the outcome that I'm interested in is stroke, and that outcome may have been a secondary outcome that wasn't the point of highlight in the abstract. The abstract highlights all-cause mortality, but somewhere in the full text, maybe I have information about stroke. And if I were to just exclude it based on outcomes at the time of abstract screening, I would be in trouble. So we try to be super careful and super sensitive. As long as we get a sense that it might be relevant, we push it forward. So we get a lot more articles to screen at the full text screening phase. Our data extraction is different. I'm going to have slides on each of these and compare them. And also how we do our meta-analyses differs. So first, just to tell you a little bit about the search strategies. These, they come from McMaster University. We have a department that dedicated a lot of time, Hyrule, for coming up with search filters for different study designs. So they have search filters for randomized controlled trials. They have search filters for prognosis. And whenever we're developing our search strategy for questions of prognosis, when we work with an information specialist, they don't only just think about the mesh phrases for the population, but they also try to add some of these terms to the search strategy. And so these are for OVID, and they have equivalents of these for PubMed. Top is Medline, the bottom is Embase. And they've developed different strategies. So you could do a strategy that maximizes sensitivity. So if there's anything that remotely resembles a prognosis question, you can include it. But the problem is that it's not so specific. So you might have a lot of garbage. You're going to have to screen a lot of articles. And believe me, so in systematic reviews of therapy, at most 6,000, 7,000. You know, COVID was crazy, but other areas, when you do it, when I see my colleagues do them, they usually are hovering around 3,000 titles and abstracts to screen. For us, it's very unusual to get anything less than 10,000 citations to screen for a prognosis question. So they're crazy, and by the time that they're done, we're exhausted. There is a strategy that is not so recommended that maximizes specificity, right? So if you implement these, for sure, you're going to make sure that they're prognosis designed, but you're going to miss a lot of other articles because the sensitivity is only 52%. And then we have a strategy that's a best balance of both sensitivity and specificity, and it's here. So I'm sure you guys are going to have these slides, and if you wanted to, I also have the link, and you can also find the terms for other study designs like randomized controlled trials, diagnostic tests, et cetera, et cetera. Okay. Then for data extraction, so for overall prognosis, when we're extracting our data, we don't have any information on intervention or exposure. We're not trying to capture who was in the intervention arm, who was in the control arm. We don't do any stratification like that. We do most of the information about the baseline demographics of the patients and most of the baseline therapies that the patients were on. So there is no differentiation. It's just a matter of being able to communicate to your audience who are the patients who made up these cohorts, so that when they're trying to use this evidence for their own patient population, they can see if their patient fits into the characteristics of these studies that have been included in the systematic review. So this one, I would say overall prognosis by far has one of the most easiest data extraction processes. The other thing that we also capture in there is just the risk of the outcome, so the number of people who experience the outcome and the total sample size of the cohort. For prognostic factors, it's similar, but a little bit different than therapy. So here now, we don't talk about intervention and comparator, we talk about the exposure group and the comparator group. So maybe the exposure would be folks who are living with diabetes, and the non-exposure group would be the folks who are not living with diabetes. Hypertension versus non-hypertension.
It's a question.
Yeah.
It's a question from Nancy.
Oh, yes, good morning for everybody. Good morning, Farid. I was looking at your slide before when you are doing your search, since you are talking about prediction models and you are working about the filter type, would you prefer the sensitivity over the specificity since you are working on prediction models?
Yeah, excellent question.
Thank you.
That's a really good question, and I can say from my experience, there are times that I feel that there's not a lot of prognosis evidence, and we have a sense of intuition as to what's happening in the field. Maybe we are in an area that doesn't have a lot of prognosis evidence, or we feel that prognosis evidence is not too large in volume. That sort of a situation, I highly always maximize sensitivity, because if there is anything, I want to make sure that it happens. But maybe I'm in a field that for many, many, many years, people have been doing prognosis studies. And that's where I would do a balance of sensitivity and specificity. I would never do the high specificity one. We just have it to show that you could do that if it's good. But there are folks who would argue for the maximum specificity, but in my practice, I only either do maximum sensitivity or the balance. And the reason is, for example, I did a systematic review. So the systematic review that we did for informing the baseline risk in the transcatheter versus surgical aortic valve replacement. In the end, we had 93 articles in that meta-analysis. So one begs to ask the question, what would one additional study do to the estimates that we get from that? And at the time, at the point that you get over 50 or 90 studies, it likely won't move the needle as much. We saw that with COVID as well. In COVID, there was so much evidence that came out, and you're all no stranger to this. We did a Cochrane review, and our Cochrane review had hundreds of studies, and it was 500 pages in the end. I was telling Claudia yesterday, no one's gonna read the full 500 pages, I know that, but it was longer than my thesis. But there, again, I would do the balance of sensitivity and specificity, because one, again, asks the question, if I find one additional study, is it really gonna move the results that I'm seeing from the systematic? And so that's the key difference. In trials, you know, there's not too many randomized control trials, so, oh my God, it would be terrible if you miss one single randomized control trial. But in prognosis, by the time that you have so many studies that when you look at the relative weights of the studies in your meta-analysis, it's not that one study is like 40%, the other is 1%, the other is, but they're very balanced in their weights because a lot of them are large sample sizes. So the relative weights that are assigned to each study is very close. So one more additional study likely not going to make a huge difference in the results of the meta-analysis. Great question. Okay, so for prognostic factors, we want to, and I got to say something about the prognostic factors. There's two ways of doing them. One way I always do, the other way I don't recommend unless it's super necessary. And I'm a hypocrite for saying that. Because you could do a systematic review of prognostic factors only looking at one single prognostic factor. Right? What does that mean? So you could say, I only want to look at the effect of diabetes. I only want to look at the effect of hypertension. Anybody want to guess what the problem with that is?
Everything is multi. How can you separate only the
Huge publication bias issue. Huge publication bias. When you focus on an individual prognostic factors, it is going to be super difficult for you to identify all the studies, even the ones that maybe their focus was on the association of diabetes, but they didn't find diabetes to be a super interesting prognostic factor. So the ones that do get published in the end are the ones that found diabetes to be super interesting. And then you would be lucky if you find articles that diabetes was one of the other factors that was in a multivariable. And maybe they report on it there. The other way that you could do it is to say, okay, I'm interested in people who have cardiovascular disease, maybe heart failure, and I want to look at every single prognostic factor in this population. And then you effectively, in these systematic reviews, why the reason they become so massive is you make a database, you make a repository of every single prognostic factor that's ever been evaluated in that population. The reason that I'm saying I'm a hypocrite is because I did a COVID review, it was a Cochrane review looking at the relationship between obesity and the COVID-19 outcomes. But then again, the way that we did our screening tried to prevent against the issue of publication bias. Any study that looks like they're looking at COVID-19 patients and prognostic factors, we included to look at the full text to see if they're reporting on obesity. But anyways, that's why I wanted to make sure I mentioned this, because this first line is mostly applicable to when you're looking at a single prognostic factor in the systematic review. But you also want to have details of what is the prognostic factor, what is the definition of the factor. If they're saying diabetes, exactly what that is. Type 1, type 2. How do they diagnose it? Is it the same across the studies? If it's, for example, hypertension, how is hypertension being defined and measured? So we need to be very clear about the definition of the prognostic factors. The other piece of information that I always encourage folks who are doing systematic reviews of prognostic factors is to capture what was the prevalence of the prognostic factor. See, in your data extraction, we capture information about the prevalence of different characteristics of the cohorts, their baseline characteristics. We might capture how many women were in a cohort, how many folks had, for example, comorbidities like hypertension, diabetes. But maybe they find a super rare prognostic factor that they're reporting on. We still should try to capture the prevalence of that prognostic factor. It's super informative and helpful for your audience to know, because maybe I can look at a prognostic factor that increases the risk by 5-fold, like an odds ratio of 5. Super important prognostic factor, but it's only present in 1% of the cohort. Its relevance drops. I mean, for that 1% who have the prognostic factor, it's super relevant. But in the grand scheme of things, and for decision makers, policy makers, not super important. So it's important for us to have a sense of the prevalence of prognostic factors. And then for prediction models, most of the information, again, we extract on the baseline demographics of the cohorts, and then we extract information about the details of the model. So what was the outcome that the model was predicting? What different prognostic factors made up the model? And then we also try to capture whether the model is operating based on measures of association, or they did a point-based system. Right? The difference is with measures of association, the model output likely is a probability, but with a point-based system, it's not super helpful. It's reduced down to saying, okay, well, because your patient had X, Y, Z characteristics, they score 3. Like CHADS-VASc, for example. CHADS-VASc is a model that predicts the risk of stroke in patients who have atrial fibrillation. It's a 9-point-based system, right? If you're a woman, you get 1 point. If you had a previous history of stroke, you get 2 points. So in the end, your patient's classified on a scale of 9. How many points did they have out of 9? It doesn't tell you what the probability was. The only way that you can get the probability is if you go back to the original derivation study of CHADS-VASc and say, okay, well, folks who had 3 points, their average risk of stroke in the next year was, for example, 6%. Yeah. Okay. Is this clear so far? Any questions? So with regards to the results of the included studies, like I mentioned, for overall prognosis, we typically look at the total number of patients who were included and analyzed in the cohort. And then we look at the number of events that were observed, because this is what gets us the measure of risk that we use in our meta-analysis. Sometimes we want to look at an incidence rate. And so when we're looking at incidence rate, for example, how many patients will experience the event if you follow 100 people for 1 year? For that, we need a measure of their time of the outcome or the median follow-up of the studies. There is a very new nifty technique that we have, and I'm a huge fan of this. In fact, some of our grants are related to this approach, where we now are able to extract a lot of information from published Kaplan-Meier curves. A super smart woman, Patricia Guyett, back, I think in 2016 or 2015, she developed an algorithm where if you digitize, and what digitize means is for every single time point that's plotted on the Kaplan-Meier curve, if you get the probability plotted in the Kaplan-Meier curve, you can feed this into her algorithm, and our algorithm will simulate an individual patient database, which then you can use to do an individual patient data meta-analysis. I will show you some examples of this. And then we're now trying to develop meta-analysis techniques around all the information that we get from these published Kaplan-Meier curves. Prognostic factors, we definitely want to have information about the outcome with which the prognostic factor is associated with and what is the measure. So we say, for example, stroke, what do you mean by stroke? Is it ischemic, hemorrhagic? And if you say bleeding, is it upper GI, lower GI, major bleed, minor bleed? It's very important for us to have the definitions mentioned. And if you say, for example, deep vein thrombosis, how was deep vein thrombosis diagnosed? If it was based on, and this is also information that's super helpful to have when you're doing your risk of bias assessment. So if you extract it, you can also make your risk of bias judgments a lot easier. If people are saying, oh, this patient has deep vein thrombosis, and they do it based on discharge codes, right? The administrative people putting that information into the patient's chart, not as good as a study that prospectively did ultrasounds on the patient, and they had adjudicators who were blinded to the measure of the prognostic factor, and they were able to say this patient has deep vein thrombosis, right? So the way that they're measuring them, also critical information for us to capture. We also want to capture, this may be obvious, but the measure of association between each prognostic factor and the outcome. And so we may have odds ratios, risk ratios, hazard ratios. And you may be wondering, well, what do I do when I have some studies reporting odds ratios, some studies reporting risk ratios, and some studies reporting hazard ratios? We've figured it out, luckily. So when your event rate is low, right, odds and risks are very similar. So if you're operating in a systematic review where the risk of the event is less than 10%, you can use odds ratios and risk ratios interchangeably. They become problematic when the risk of the event is high. We had this experience because we're looking at prognostic factors for recovery in children who are malnutritioned. And recovery, the risk of recovery it's not a risk. The proportion of children who have recovery is high, it's like over 50%, which is good, but you want it to get better. 50% is considered low in that case. But when you're operating with 50% probability of an outcome, then odds ratios and risk ratios are not similar. We have formulas that can help you convert from odds ratios to risk ratios to odds ratios. What it does need is a measure of the baseline risk. The risk of the outcome or the probability of the outcome in folks who didn't have the exposure. And sometimes it's not presented. You may have multivariable models, right, that are reporting adjusted measures of associations. So by the time that you're looking at adjusted measures of association, you don't have a measure of baseline risk. And we made a calculator that if you know the prevalence of the prognostic factor, you know its measure of association, and you know the overall risk of the outcome, you can use that information to get what would be the risk in those who don't have the prognostic factor and the risk in those who do have the prognostic factor. And that number serves as the baseline risk that you can feed into these formulas to convert between odds ratios and risk ratios, similar with hazard ratios. Hazard ratios, as long as you have the baseline risk and you know exactly at what time point you want to focus, like 1 year, 2 years, 3 years, you can convert hazard ratios to odds ratios. A lot of, I'm mentioning a lot of theory, not a lot of information on the slide, but I get so excited that it just gets me carried away when I'm talking about it. You also need to have a sense of standard error, right? The precision around the estimate that you're extracting. So you can do either 95% confidence intervals, and some studies don't report 95% confidence intervals, but hopefully maybe they report standard error, or at worst case scenario, they report a p-value. And with the p-value, if you're really stuck, there are ways, and Cochrane has ways that you can get a measure of standard error if you only have p-values. Sometimes you don't get any of these, right? Sometimes you're stuck in a situation where folks come to you and say, okay, we looked at diabetes, no significant association. They don't tell you what the measure of association was. They don't tell you what the odds ratio was. They don't tell you what the 95% confidence interval was. So we do missing data imputation in this case, where we say, worst case scenario, when the authors say diabetes was not associated with the outcome, let us say the odds ratio or the risk ratio or the hazard ratio was 1. Now, what do we do for the standard error? We borrow the standard error from another study that had very similar event rate and sample size. It's an imputation technique. And then we do sensitivity analysis at the end to see if the results of our meta-analysis differs when we remove the studies that we imputed on versus the studies that gave us all the complete information. Is that clear? We call this approach the hot deck approach, where you borrow the standard error from a very similar study.
Hot deck.
Yeah, HOT space DECK. I mean, we try to do different things before we get to that point, like contacting the authors. Those are standard practice. I'm assuming we all do that before we get to this point. This is like worst case scenario. They haven't responded to you. Paper was from the 50s. Author is not alive. You got to do something. Okay. And the other key thing for prognostic factors, it matters what other factors may have been adjusted for. Sometimes there was nothing adjusted for, so it's an unadjusted study, and we can talk about that a little bit. I'm not a fan of using unadjusted associations because they're not really helpful in clinical practice. You're overestimating the risk. It's not really accurate. So I always try to go for adjusted associations. And when you're going for adjusted associations, you need to have a sense of what other factors were adjusted for in that study.
There's a question from Dr. Munoz. He wants to know, do you extract the OR or the R risk from univariate, multivariate analysis progress?
This is exactly, okay, so let's go into it. So when I do systematic reviews of prognostic factors, I focus on multivariate associations. We talked about this in grade guidance 28. Prognostic factors, there's 2 scenarios for their use. First scenario is that a single prognostic factor is as good as a multivariable model. An example of this is D-dimer. D-dimer for predicting who's going to have deep vein thrombosis. It's equally good as compared to using the Wells score, which is a multivariable model. Well, if it's equally good, you can just use D-dimer alone by itself. And if that's the case, you only need the univariable association. D-dimer doesn't need to be adjusted for other factors because it's performing just as good as a multivariable model. That scenario, we believe, within the grade prognosis working group, we believe it's super rare to come across someone like this. So by the point of care, when people are using prognostic factors, they're using multiple prognostic factors in combination together. So if I'm to be talking to my patient, I would say, okay, you have hypertension, you have diabetes, you have your age that's over 50. I have a measure of association for each of these. If I have unadjusted associations for these 3 factors, I'm going to be always overestimating prognosis in my patient, overestimating the risk in my patient. When I have adjusted associations, the associations have been adjusted for the other covariates. Maybe the association of age has been accounted for and controlled for hypertension, diabetes. And that allows me to do multiplication of these measures of association to then use in estimating prognosis in my patient. And that's what we believe is more common, where multiple prognostic factors are used together. And when you're using them together, you need adjusted associations. So at the point of doing these systematic reviews, I keep that in mind, and I'm always extracting adjusted measures of association. Unless, again, I know that there's one single factor that's as good as any other prediction model that's out there, which is super good. Excellent. And the reason that we need to extract information about the other factors that have been adjusted for is because the differences in how well the studies have adjusted for these other factors may explain some of the heterogeneity that we see between the studies. Maybe one study adjusted for hypertension, the other didn't, right? Maybe 3 studies didn't adjust for hypertension, 3 did. That could be a potential source of explanation for the between study heterogeneity that we observe for the measures of association. between the prognostic factors and the outcomes. And sometimes we find ourselves in situations where it doesn't matter what they adjusted for. When we have like a forest plot of 10 studies, the point estimates are very similar to each other. The studies adjusted for different things. So that tells us that those other factors didn't really confound the relationship between the prognostic factor and the outcome. Yeah. Is there any other questions?
Yes.
No, 5 seconds. Any questions from the group? Is this clear? So for prediction models, we want to extract information, and again, we're talking about results. So when you're talking about discrimination, we either extract information on C statistics or concordance statistics or the area under the curve. And for binary events, these two are interchangeable. So you can combine both of them together. We also, again, try to capture the 95% confidence interval, the standard error, or the p-value. And again, if this information is not provided, there are formulas that Cochrane Prognosis has put together. So Richard Riley, Carl Moons, these are some of the big names in Prognosis, colleagues from Prognosis Group, the Cochrane Working Group for Prognosis, and they have guidance documents for how to do systematic reviews of prognostic factors prediction models. And in their guidance documents, they do provide you with formulas so that when studies don't report their 95% confidence intervals, you can estimate what the confidence interval should have been in that case. And then for calibration, this is a very controversial area because the practice of reporting calibration across studies is not standardized. The best way is for you to see a calibration curve where for every single observed risk group, you have the predicted probability plotted, and you can see whether the model is overestimating or underestimating. But oftentimes what we're stuck with is the overall risk of the outcome and the overall predicted probability. And so we get this observed to expected ratio, which is a single number. It's not a really good measure, and I'll talk about it a little bit more towards the end of our talk. But so this will be a narrative summarization of what you're seeing with the calibration models. With the calibration curves, at the moment, we don't have a good way of pooling them. So the only thing that we could pool is the observed to expected ratio. Yeah. Okay, so meta-analysis wise, for overall prognosis, like I said, you usually have proportions. So you would have the number of events on the numerator. The denominator can be a person risk or the total number of patients in the study. And then we would do what is called a meta-analysis of proportions. And there are packages that help you with doing this. So if you're operating in R, MetaProp would be the library that you would use. In Stata, there's also MetaProp that you could use. And the really good thing about using that, the reason you can't do meta-analysis of proportions outside of these libraries is because you need to account for the fact that people can't have a negative probability, right? So you can't have a standard error that is equal distance from the point estimate on both sides. There is a lower limit to the confidence interval, and you can't go less than 0. So these packages account for that. They do a binomial distribution or they other techniques for accounting for it. And the other thing is, a lot of the times, just because a study is reporting low proportions doesn't mean that it deserves less weight. In systematic reviews of therapy, if a study is reporting lower number of events, right, you're going to give it less weight. The weight is determined by the number of events, which drives the standard error. In proportions, we don't want that to be the case. Maybe the truth is truly that the prevalence is really low, right? We don't want it to be giving a lot of weight to the higher proportion studies and not so much weight to the lower proportion studies. So there are techniques like the Freeman-Tukey transformation that these libraries have that equalizes the weight across the studies. And it becomes even more balanced so that you're not putting a lot of emphasis on the large event weight studies. Is that clear? That's a pretty important point here. Yeah?
Nelson has another question.
Yeah.
Well, thank you. Farid, when you are calculating the proportions, why is that for the denominator you are using the mean follow instead of median? For example, you have very different follow-up times across the studies. Is that correct? Or
Yes.
you can use only the mean, or you maybe want to use the median in that case? What is your criteria?
Excellent. So this proportion we're calculating once per study. So the average follow-up time or the median follow-up time you're getting from the specific study, right?
Okay.
To use in the calculation. So if a study is reporting median follow-up time, we use median follow-up time. If they report mean follow-up time, we use mean follow-up time. Unless we really believe that for some reason the two measures are not equal, so they're going to be completely different. And as a result, then we try to convert the mean to the median if possible and the information is available.
Okay, thank you.
Yeah, great question. Great question. Great point. And then the other newer technique that I was telling you about, this is the work that the story is, I was in my master's at the time. And I got tasked with doing this overall prognosis systematic review. And there were 93 studies. This is the surgical aortic valve versus the transcatheter aortic valve one. And every single line that you're seeing here is one individual study. So the way that, luckily we found the algorithm by Patricia Diet, which her code works in R, so we implemented it. We extracted the probabilities for each time that was plotted on the Kaplan-Meier curves. We fed it into the algorithm that she had, and we were able to reproduce the individual patient data that created every single Kaplan-Meier curve. Her algorithm is shockingly accurate, shockingly accurate. If you know the number of events, if you know the number of people who are at risk at each different follow-up time, and you have the published curves, you can simulate the individual patient data, and it produces a exact replica of the curve that you saw in the publication. What we then did was to do, we just did a survival analysis of the combined data sets. So we stacked the databases. We had 93 studies. Now we had 93 survival data sets. We stacked them together and we produced this meta-analysis, quote unquote meta-analysis. It's not your traditional meta-analysis because we don't account for clustering of patients. Kaplan-Meier curves, they don't have a way for you to introduce a random effect term to account for the clustering of the patients. The confidence intervals you see, I didn't produce confidence intervals here because they would be misleading. There's suspiciously narrow, again, because you're combining all these different data sets as if they're all coming from the same cohort, but they're not coming from the same cohort. And that's what our grants are on at the moment, where we're now trying to create a new way of doing Kaplan-Meier estimation, where at every point that you're calculating your survival probability, you're in fact doing a meta-analysis of proportion and then plotting the curve. So hopefully we can produce some new libraries for meta-analyses. And this would be super nice because the problem with these proportions is that you assume a constant event rate, right? Risk of stroke is huge after cardiac surgery, but the longer you go away from cardiac surgery, your risk of stroke comes down. Your hazard is high after surgery, comes down afterwards, right? You don't capture all that information with a proportion, but you do capture it with survival curves, where the survival curve can show you that the hazard is very high early on in the follow-up period, and then if it becomes flat, that's telling you that the hazard has subsided. Right, so a lot more granular information in these curves. Is this clear so far? This one? So you see how like there's many, it looks like someone had a messy hair with a comb. These are, each of them are individual studies. And then we, the way that we're plotting them at the moment is that we've stacked all these into one data set. So we had 93 different data sets that we obtained after using Patricia's algorithm. And then here is just us doing an overall survival that was stratified by the age. So this is the median age of the studies. Sorry, I didn't talk about this in more detail. One of the subgroup hypotheses that we had in the systematic reviews of overall prognosis is that your age can lead to completely different estimates of mortality in this patient population. So we had some studies in which the median age group was less than 65, some that were between 65 and 75, some that were between 75 and 85, and some that were over 85. So this is a between study subgroup analysis because we're using the average age of the cohort or the median age of the cohort to do this stratification. But this is, in essence, the possibility of doing this is by combining every single 93 studies that you're seeing in the upper graph. Yeah?
Wouldn't that be the prognostic factor study? Like, that's an
Excellent question. Excellent. So you're jumping ahead to subgroup considerations. Let's put a pin on it, and I'll come back. I have a specific slide just to that question. Okay. Are there any questions in the chat that I should?
How do you handle in overall prognosis differences in net survival, relative or cost specific versus overall survival? Many population-based studies now use relative survival. How do you handle in overall prognosis differences in net survival, relative or cost specific versus overall survival? Many population-based studies now use relative survival.
Right. So that's a good question. That's a really good question. We came across a scenario that one of the outcomes that we looked at was, for example, the risk of deterioration of the valves, the artificial valves that get implanted into the aorta. And we call this event structural valve deterioration. It's a very cause-specific outcome. You can't experience this outcome if you're dead. So mortality competes with it. And this became a risk of bias issue for us because we found that a lot of studies were ignoring the competing risk here. And so rather than doing cumulative incidence functions or cumulative incidence graphs, they were just doing Kaplan-Meier graphs. And we had other studies that were doing cumulative incidence functions that was getting to the cost-specific risk and accounting for the competing risk. And so we consider that as a risk of bias issue. We had to consider that as a risk of bias issue. But again, to get more specifically at that, it's a matter of the question that you're asking. It goes back to your research question and the outcome that you're interested in. And if you believe that the outcome is competed with and you need to have cost-specific estimates that account for competing events, then it would be a risk of bias issue if the other studies are not accounting for it. Is that answering the question?
Is there?
Yes, that is the issue. Thank you.
Excellent. Great. Okay. For prognostic factors, so the information that we work with, how much time do we have?
15 minutes.
50. Excellent. So with prognostic factors, we work with the natural logarithm of the hazard ratios, odds ratio. I always tell this to my students. Odds ratios, risk ratios, hazard ratios, they're on the exponential scale. You can't do linear algebra. You can't do linear math on something that's on the exponential scale. So whenever you're working with these measures, you need to take their natural logarithm, so you bring them to the linear scale, and then you can do math. You can do the algebra that's necessary for meta-analysis. So we always convert to lons, and then we have the respective standard errors, and then we pool the lons of the outcomes. And whenever you're doing a meta-analysis, you want that meta-analysis to be for a specific prognostic factor for a specific outcome, right? So if you have a bunch of studies looking at diabetes, and some of them are looking at diabetes for strokes, some of them are looking at diabetes for mortality, you can't combine those. You have to do stroke separately, you have to do mortality separately, right? And then sometimes, if you can convert between hazard ratios and risk ratios, most ideal to do that. But it is sometimes reasonable to say that if a study is telling you that their proportional hazard assumption was met, that means that the hazard ratio was exactly the same whether you're looking at 1 year, 5 years, 10 years in the follow-up period. And it's sometimes reasonable to just combine it with the ln of the odds ratios and the risk ratios. So these are some examples. This is an example of looking at the association between the age of the recipients at the time that they're getting their kidney transplant and the risk of losing a kidney graft at 1 year after transplantation. And then when we do a systematic review of all prognostic factors, and you have multiple different meta-analyses, we do these summary forest plots where each of these different lines is one single prognostic factor that we were able to meta-analyze. Sorry, it's a little bit small, but hopefully when I share the slides, it'll be massive on your screens. Any questions here? No? And okay, so for the meta-analyses of prediction models, there are library packages for doing meta-analyses of C-statistics or area under curve. And this again was developed by the Cochrane group, the libraries for R. And so you would do one meta-analysis for each outcome for each model separately. And so this is an example. This is the CRB65 model. This is a model that predicts the risk of pneumonia. And so you had all these different studies that reported on the C statistics. You see these bars that are super wide. That's where the study didn't report the standard error, and so they had to impute what the standard error was, which is why it's so wide, because it's being super conservative. And then you get a pooled estimate for what we believe is the best guess at the discriminatory statistics of the CRB65 model. And then for calibration, the best practice is what I was trying to tell you, which is this calibration curve. With calibration curves, you have observed incidence rate. Observed is, let's say you have, I'll tell you what it, let's start with the predicted. Predicted is you take, for example, all the patients that your model said the risk was 10%. So you may have 10%, sorry, you have 10 people who were classified as 10% by the model. Okay, with me so far? In these 10%, in these 10 people who were classified as 10%, if 1 out of 10 experienced the event, the model is calibrated. Because the model said 10% and the observed event rate was 1 out of 10, which is 10%, right? If it's anything else, then it's miscalibrated. So it's either overestimating or underestimating. So what each individual does is a cluster of patients for whom the model set the exact same predicted probability. And now you're looking to see what was the observed event rate in each of these clusters. So here, the model, for example, said, I know you can't see it, but the model said 11% for all these patients, but in actuality, it was like 13%. So it's a bit of a miscalibration, right? So model is underestimating. Models assigning a lower risk than what we actually observed for all those patients who were classified as that risk. This is optimal because what it's telling you is that in all the different ranges that the model can predict low risk, intermediate risk, high risk. How well is the model calibrated to what we actually observe in real life, right? But again, it's not standardized practice to be reporting this. Even though this is the best way, Many individual studies don't report calibration curves, which is terrible to begin with. B, sometimes they don't even provide calibration curves. So what we have access to is the observed to expected ratio. And the observed to expected, so the observed event rate in the entire cohort and the expected event rate in the entire cohort. It's not an ideal measure, because if my model overestimates in half the population and underestimates in the other half, the average is perfect calibration, right? And that is also why it's not a good pooled estimate. And this is what our concept paper is on with Greg. And I'll talk a lot more about it if time allows. But you see how the pooled estimate is observed to expected ratio close to 1. Perfect calibration, right? Yeah, well, half is like overestimating and the other half is underestimating. That's why on average you see your good calibration. Whereas the truth is the model is completely miscalibrated in all the different cohorts that it was applied to. Right?
So then why should you use this calibration if it can give the pay from?
Concept paper coming up. So in our concept paper, this is a necessary evil. This is all we have to work with, but we have some conceptual clarities as how we can make inferences depending on the totality of what we're seeing here, as opposed to just focusing on one single estimate at the bottom, which is the pool estimate. And I'll show you that towards the end. We're nearly to the concept paper. Okay. All right. And subgroups. This is the question that. So in overall prognosis, we don't have subgroup. There is no effect to be modified, right? I don't have a measure of association. I don't have a risk ratio or odds ratio. I'm not trying to see if in one group the association is stronger and the other group is weaker. There is no association to your point. So whenever you do division of studies based on factors, you're doing a between study assessment of a prognostic factor. Because you're looking at a factor that modifies overall prognosis. And a factor that modifies overall prognosis is by definition a prognostic factor. A subgroup is by definition a third factor that modifies the relationship between your exposure and your outcome. Right? We don't have an exposure and an outcome in overall prognosis. We only have one factor that modifies your outcome, which is prognostic factor. So this is a new essential clarity that we need to start to implement when we're doing systematic reviews of overall prognosis. Because a lot of people just say, oh, we did a subgroup analysis. You didn't do a subgroup analysis because there was no effect to modify. Okay? So this, to your point, this is a prognostic factor, but it's a between study assessment of a prognostic factor, which is interesting. So, I mean, we're seeing it here, but the credibility of it is slightly decreased because, we're saying that the median age of the cohort was 65, but just because the median age of the cohort was 65 doesn't mean that everybody in the blue curve was less than 65. There may have been people in this blue curve who fell into this category, right? So that's one of the limitations here.
Oscar has a question.
Yeah.
Yeah. Do you listen to me?
Yes, we are.
Yeah. I have a question about the calibration evaluation when you are using observed or expected number of events, especially because different studies have different sample size. And as you said, in different basal risk categories, there are different rates, observed or expected rates. So have you considered to combine it and to present the information for different basal risks in a graphic and to show the sample size with, for example, the sample of the dots or something like that? Because presenting just the observed or expected rate seems too weak for me.
Brilliant point. Yes, we did do that, and I'm hoping to show you that in the concept paper that I would like to present at the end. One of the intuitions that we had when we looked at this evidence is that In some papers, it is showing good calibration. In some papers, it's showing underestimation, and some is showing overestimation. Could this be related to the baseline risk or that overall risk in the cohort? And so one of the, I just said don't call it subgroups, but I'm going to call it subgroups. One of the subgroups that we did here, for lack of a better word, is based on the overall risk of the cohorts. And I'll show you that later. And it nicely turned this very heterogeneous figure into more sensible estimates where we know in what risk the model is working and in what risk is not working. So it was like in the low risk groups, the model overestimated. In the intermediate risk groups, it was calibrated. In the high risk group, it was underestimated. And we saw that once we implemented the subgroup that you're referring to, which is a great point. Okay, and then for prognostic factors, this is a traditional subgroup, right? Because now you do have an effect that you're modifying. And then for prediction models, again, there is no effect. It's very much like overall prognosis. With overall prognosis, we can call it prognostic factors. I just don't have a better word to call it other than subgroup. That's why when I went back to the previous slide, I ended up swallowing my own word here and said, oh, it's subgroup. But at some point we'll come with a better term for what's happening with these ones. Because again, there is no effect, right? That's being modified. This is the definition of a subgroup. Okay, quick note about risk of bias. I just wanted to make sure that you guys are aware of this. So QUIPS is the long-standing tool that's been around for prognosis. It stands for Quality in Prognostic Studies, and we've been traditionally using it for our risk of bias assessment and overall prognosis and prognostic factors. It comes from, again, Cochrane Prognosis. And for prediction models, we have PROBAST, which stands for Prediction Model Risk of Bias Assessment. But I just wanted to let you know that in the upcoming near future, they have been working on QUIPS 2.0, which is now going to be a lot more comprehensive for prognostic factors. ROBOPS, risk of bias of overall prognosis, is now going to be a tool that's specifically dedicated for overall prognosis studies. And the reason that it's needed, because here with QUIPS, we're asking information about how the prognostic factor was measured. And so a lot of people have to end up modifying QUIPS when they're doing overall prognosis. So Cochrane realized this, and they are now dedicating a full specific tool to overall prognosis. And I don't know about you guys, but every time I open a journal, there's something about machine learning and artificial intelligence. And those are a form of modeling as well. So we're also developing PROBAST that's specific for artificial intelligence. And that's coming down the pipeline as well. I'm going to, for the sake of time, I'm going to skip through these, which are the different domains for the QUIPS, and I just wanted to jump here to the latest concept on grade. Is that okay? How much time do you have?
35.
30, excellent. That's more than it. So, I gave an introduction to calibration because I got so passionate about it as we were talking. But again, it's the commonly used definition that we have for calibration. And that's what our concept paper is on. We focused it on calibration. For patients whose risk is 30%, a model will be calibrated if on average 30 out of 100 experience the event, right? So if you have 100 people classified as 30%, and you see that 30 out of 100 are experiencing the event, then whatever the model is assigning to this group of patients, it's accurate. There's different hierarchy of approaches to assessing calibration. We briefly talked about this, but I wanted to give a formal definition. This comes from Ben Callister. He's one of the experts in prediction models and calibration of prediction models. He had a wonderful paper, bit dense at points, but really good read, where you have calibration in large, and that's the observed to expected ratio. Then you have a weak approach to assessing calibration, moderate, and strong. So what are these? Just to give you a sense, calibration at large is our observed to expected ratio that we talked about. So it's about the entire cohort. There's not much to it. You have the total observed event rate, and you have what the model said for everybody in the cohort, and you take the average of that, and you see how much they agree with one another. A weak assessment of calibration is, it's related to a calibration curve, but you're fitting a logit function. So you're trying to turn a calibration curve into a linear function, and you're trying to see where the y-intercept is, right? If the y-intercept is at 0, that means that when the model says the risk is 0%, the observed event rate is 0%. If the model says the risk was 10%, the observed event rate was 10%. So you're trying to turn something that may not necessarily be a linear function into a linear function, and that's why we call it weak, right? And this A is the intercept, so when your A is over 0, you're underestimating the risk, and when your A is less than 0, you're overestimating. This, what we call underestimation or overestimation, really depends on what we label the X and the Y axis. And so the X axis would be what the model predicts, and the Y axis is what the observed event is. Okay. The modern approach for calibration, and this is what we are trying to get everybody to do, but there's no standardization, is truly this calibration curve, where, as I said, you can see that for the lower risk group, the model seems to be overestimating the risk, and in the this section, it's underestimating the risk. And there are some points that it is calibrated, but it's telling you at different points what's happening with calibration. It's very granular. This is a unicorn. This will, I would be surprised if you see it. I would love to hear from you if you ever see it. But even McAllister calls this a unicorn because this is now, your database has to be so massive that you're saying, okay, across individuals will have the same pattern of prognostic factors. So people with the same age, with the same comorbidities. Does the model predict the risk accurately? So in essence, you're doing a separate calibration curve for people with different patterns of prognostic factors that make up your prediction model. And so this is an example of a miscalibrated model where for folks with different patterns of prognostic factors, it's all over the place. You'll never see this. This requires sample sizes of millions or something to be able to do this sort of analysis. That's why we're trying to settle for this. It's a very stubborn community to try to move. So it's very tough.
Do machine learning can give this?
Machine learning people, we have some of the best machine learning papers that I've seen, they don't even report on calibers. And so it's like what I'm experiencing with artificial intelligence, and I would love to hear from everybody else if you feel the same sentiment. It's like we have to go back to square one and start with evidence-based medicine all over again. It's this fancy new technique that everybody thinks they can do magic and solve everything. But there's standards that we've come up with over the years that are just now being ignored. And so most of the time they just stop at discrimination, or what they call confusion matrix, because they didn't like our terms for model performance like discrimination. Yeah, and they don't do area under the curve, but they do receiver. No, they do like something else, which is related, but slightly different. The name is blanking me at the moment. But they very, very, very rare. I've seen a machine learning paper develop a model and assess its calibration. The other problem is that a lot of machine learning models, they stop at internal validation. Right? Why do you do machine learning? You do machine learning to look at very high dimensional data, right? Like images that you've obtained from patients. Or you do, you could do genetics, you could do, for example, the audio signals that you might get from the heart. It's meant to be with higher order data, not just numbers. That's where machine learning shines, because now it can use that information. We can't use images, we can't use audio, video in traditional biostatistics model. Machine learning has a way of turning those high dimensional data into numbers that it can't do algebra on. That's where it shines. to get access to that data, you need a massive research infrastructure, right? Like I'm talking millions of money going into your research institute for you to get access to this information. I cannot tell you how much money we spend in Canada to try to get this information. We have some really rich families who pay for this. I'm getting recorded. This is terrible. But the problem is that when you get such unique data, where are you going to validate your model? Who else has this data? So a lot of them are stuck with internal validation. And they don't even think about calibration, right? Like so, and then you try to get into arguments with them. It's like, oh, you got to take time to do your assessment of the model properly before you implement it into clinical practice. And the standard response that you get is, we don't have time. By the time that we do all this, our model is going to be outdated and irrelevant. So it's fun. I don't know. You can see the struggles in the way I'm talking about. But so is this clear about calibration? Excellent. So the first concept or consideration that we came up with in great concept 2 is that we need to be super clear about what it is that we're rating our certainty in, right? And this isn't new. Monica Holkrantz, who's a great member, you know her. She wrote the paper on what is it that we're rating our certainty in, and from that moment on, that was a new essential clarity for grade, because before that we didn't know what we were rating our certainty in. But now we're very explicit that when we say high certainty or low certainty or moderate certainty, that is about an inference that we've made from the results that we're observing. So with what is it? What are we rating uncertainty in? In interventional questions, we're doing it on benefits and harms. We could either say if there's any effect with an intervention, important effect, a particular magnitude of effect. With prognostic factors, it depends if you're doing it in a contextualized or partially contextualized. So this is if there's any prognostic value, and this is about the absolute risk differences between those who have a prognostic factor and those who don't. And then for diagnostic tests, we're rating our certainty in how accurate a test is for diagnosing an underlying condition. And for prediction models, in our group, we said it's either a satisfactory or unsatisfactory model performance. Okay, so what does that mean? Satisfactory would be if across the different studies that were included, the observed to expected ratio, despite its massive limitation as a measure that I was telling you about, it's close to 1, suggesting satisfactory model performance. We specifically refrain from saying calibrated, because if I see an observed to expected ratio of 1, I can't say for sure it's calibrated. Because like I said, in a single cohort, if the model overestimates in half and underestimates the other half, on average, I'll see an observed to expected ratio of 1. So at best, maybe it's satisfactory model, but I can't say it's calibrated. And then we said if your observed to expected ratio is anywhere from 0.9 to 1.5, this might be considered satisfactory. But where you draw your thresholds is really dependent on your clinical context and how much miscalibration you can accept, right? Like if your decision thresholds are within 5% margins, this 0.9 to 1.1 is not going to be good for you. That's going to be unsatisfactory. So if you need to accurately predict within a 5% range, then you might go from 0.95 to 1.05 for what you would consider to be a satisfactory model performance. Unsatisfactory is where across different included studies, it's far from an observed to expected ratio of 1.0. Okay.
I have a question, but in a different cohort, the same model will perform different. Like the calibration is always going to be different according to the cohort.
Exactly. But this is yes, you're right. You may across different cohorts, you may observe different results and different performance. But this is what we're deciding ahead of our assessments, right? Of what we call satisfactory and unsatisfactory. As somebody who is now considering the use of the model, I need to define the boundaries in which I'm operating. And after I've decided on my boundaries, then I go to look at the evidence and say, okay, across all these different studies, it didn't really fit my definition for satisfactory model performance. So I'm not so happy with the model that's in front of me. Does that make sense?
How do you decide the cohort?
How do I decide on
The cohort.
the cohort?
That you're calibrate?
So, sorry, not being clear. I'm not being clear. I care about my practice, right? So I'm trying to decide on the use of a model in my practice. And in my practice, I know that I need to be accurate within 5% of the actual risk of the patient. And so that's, for me, in my area, I'm defining the parameters for what I call satisfactory and unsatisfactory. Once I define this definition, then I go to the cohorts that validated the model and see if it fit into my satisfactory definition or unsatisfactory definition. Yeah. So I'm not using, yeah.
What would be the number to be a moderate calibration in the observance ratio?
Good question. So when we were developing this concept, we chose a simple approach of doing a binary classification of you're either satisfactory or unsatisfactory. But we did acknowledge that people may also operate in an area where you might have multiple categorization of the performance, where you would say this is adequate performance, this is moderately adequate performance, this is weaker, and so you could do different, and you would have different thresholds for each of those. But it really depends on the context that you're operating in.
But there's no connection with the other slide that you were talking about.
This one. Okay, so yes, I should say, our concept paper is only focused on this. Only on, because we would love to do this, but we can't meta-analyze this at the moment. This is the narrative summarization of what we see here. What we can work with and what we can meta-analyze, and if you refer to that CRB65 model that I was showing you a couple of slides back, what we can get across every single study is the observed to expected ratio. And so our concept is around the observed to expected ratio measure. And we're trying to, even though it's terrible, it's an evil measure, I'm going to call it. We're trying to do the best that we can with it and be careful and try to make some sense of the performance of the model in the absence of seeing this across every single model that's validated. Great point. I'm sorry I didn't mention that we're focusing on the calibration at large. Okay. Okay, so the second consideration was, and this is going to be a little bit uncomfortable at first, the inconsistency that we see across the results of the studies that are included in the meta-analysis is now informing the inference in which we're rating our certainty. All right, let me say that a little more carefully. So in grade, first you determine your certainty, then you look at risk of bias, imprecision, inconsistency, and direct dispublication facts, right? What we're saying now is, okay, before you get to all those other domains, take inconsistency first. The inconsistency is going to help in deciding the inference in which you're rating your certainty, whether the model performance is satisfactory or unsatisfactory. What does that mean? Let me show you some examples. Okay, this is what I'm trying to say. Assessment of heterogeneity normally has no bearing in terms of deciding what our target of certainty is. So in intervention, overall prognosis, prognostic factors, prognostic disaccuracies, we don't use heterogeneity or inconsistency to decide what it is that we're rating our certainty in. But for prediction models under calibration, we think it's critical. And the reason that we think it's critical is, before I get there, this is how we would assess heterogeneity. You're typically familiar with this. It's the same as any other consideration for heterogeneity. We look at the overlap of the point estimates, the overlap of the confidence intervals. In prognosis, we don't use I-squared statistics, but tau could be helpful. If it's 0, then you could say, okay, it's reasonable to say no heterogeneity. If it's over 0, there may be a suggestion of a heterogeneity. So these are some tools that we have for assessing heterogeneity. But look at this. This is the EVOL study, CRB65, for predicting pneumonia. Across the individual studies, the model is either substantially underestimating or overestimating. So observed to expected ratio. If your observed is greater than your expected being the prediction of the model is underestimated. And if the observed is lower than your expected, the model is overestimated, right? So if the observed is lower than the expected, it will be on this side. The model is overestimating, model is underestimating on this side. So you have a bunch of studies in which the model is underestimating, a bunch of studies the model is overestimating. The degree of the observed heterogeneity across these studies is telling us that the model doesn't have satisfactory performance. That's what we need. Here, what am I doing? Like, I'm looking at the differences across the studies. That's an assessment of heterogeneity. And that heterogeneity that I'm observing is now informing my inference that the model has unsatisfactory calibration. Why do I do this? This is a very unhelpful full statistics. So we need another way of determining what is our certainty, in which we're rating our certainty. This occurs once we know that any other approach to assessing heterogeneity was unfruitful, right? So maybe they had subgroup hypotheses. They tried to explore it. It didn't explain the observed heterogeneity here. With the lack of explanation of the heterogeneity, we make the inference that the model performance is unsatisfactory. All right, so here are some examples, right? The hypothetical meta-analysis. Here, the studies are consistently all hovering around 1.0. Do we agree? An example where homogeneity or your assessment of heterogeneity across the studies is telling you that the model has satisfactory performance. Here, by and large, all the studies are hovering still around 1. There is some slight heterogeneity, but you could still make the inference, the initial inference, that the model performance is satisfactory. Here, enough studies are still hovering around 1 that your initial inference is that it's satisfactory performance. Now, your certainty in that is a separate consideration. And we'll get there in a second. Some examples of unsatisfactory performance. Super heterogeneity here, right? So we can make the inference that the model calibration is unsatisfactory. Here, you only had 2 studies hovering around 1. The other ones are far apart from 1, so unsatisfactory model performance. And again, here, they're again very much away from the line of 1.0, so it's unsatisfactory performance. Clear? Once we've decided in what it is that we're rating our certainty, now we're going to use that same inconsistency as part of the other domains within grade to rate our certainty in that inference that we just made. Okay, so now we're going to be looking at risk of bias, imprecision, and direct publication bias. Inconsistency, we used it first to determine what was our inference. Now we're also going to use it for judging our certainty. And so for moving forward, I'm just going to focus on inconsistency. Let's say no issues for publication bias, no issues with risk of bias, no issues with imprecision, no issues with indirectness, okay? And again, the same criteria, overlap in point estimates, overlap with 95% confidence intervals, same criteria for assessing heterogeneity. What was our inference here? Satisfactory and monotone. Do you have heterogeneity here? And I said, let's assume no issues with risk of bias, no issues with indirectness, imprecision. So what would be your certainty in the inference that the calibration is satisfactory? So you have high certainty, and you would not rate down for inconsistency in this case. Agreed? This is a close call. Our initial inference was that the model performance is satisfactory, right? In some folks who, in their clinical context, they decide maybe the margin of error is very tiny, they might look at this and say, this is enough heterogeneity to cause some doubt about the inference that model performance is satisfactory. But in some cases where your margin of error can be a little bit wider, maybe this is not concerned. So it's a close call. Some may say serious inconsistency. Some may say not serious inconsistency. So here you would again make the inference that the model performance is satisfactory, and depending on what context you're operating in, you could say I have serious heterogeneity or not, right? In this one, again, we had enough studies hovering around 1 that we made the inference that the model performance is satisfactory. But we also have enough studies away from 1 that it creates doubt in the inference that the model performance was satisfactory. So in this case, we're saying that if it wasn't explained by any subgroup hypotheses, there's sufficient degree of heterogeneity that we would say there's serious inconsistency, and we would rate down 1 level or 2 levels of this. So far with me? This is fun. All right, this is my favorite. There was heterogeneity here that led to the inference that model. I'm purposefully standing here so you don't see the text. We made the inference that the model performance is unsatisfactory. What would you say in consistency with regards to your certainty in the inference of unsatisfactory model performance?
Inconsistency. What would you say about the inconsistency?
What would you say about your certainty in the inference that the model performance is unsatisfactory? Right. So first we use heterogeneity to say model performance is unsatisfactory. Now we looked at risk of bias, no problem, indirect risk, no problem, precision, no problem, publication bias, no problem. We're now trying to decide if we have doubts about the inference that the model performance is unsatisfactory. Yes? Yes? We disagree. It is consistently consistently unsatisfactory across the studies. This is I love the facial reactions that I'm seeing here. We made the inference based on the observed heterogeneity that the model performance is unsatisfactory. But it is consistently unsatisfactory. Right? It's not that, oh, like I have some inconsistencies. In some cases, it's like performing well. In all cases, it's miscalibrated. In all cases, so it is consistently unsatisfactory model performance. So the heterogeneity informed our inference, but here we're not rating down for inconsistency because it is consistently bad. I'll show you some more examples. Okay, let's look at this one. Here, we make the inference that it's unsatisfactory model performance, right? Because by and large, a lot of the studies were away from 1.0, but there's some studies that were close to 1.0. So in the inference of unsatisfactory performance, I now have some doubt that in some cases they may have unsatisfactory performance. So now I'm rating down for my inference that the model performance is unsatisfactory. Where would we have, again, high certainty? Look at this one. It's unsatisfactory, but it is consistent. Again, it's consistently unsatisfactory. There is a difference between this, and I'll tell you what that difference is. The distribution of the point estimates has bearing on implications for future research. Here, I can do a simple fix. I can recalibrate the model. Right? I can recalibrate it and bring it closer to satisfactory performance. Here, I'm screwed. It's consistently telling me that the model performance is bad, but I need to go and develop a whole new model to fix this. I can't, there's no simple recalibration that can fix this. So both of these are for performance, both of these high certainty that they're for performance. I can do something about this. I can't do something about this. I'm gonna take a massive pause here and allow you to digest and ask me questions.
Like, this was consistently underestimating the effect. So it's
Exactly.
just like
Exactly.
changing the scale.
Exactly. But here, it's again consistently unsatisfactory performance. It's not consistently underestimating or consistently overestimating. If it was consistently underestimating or overestimating, I could fix that. It's consistently just telling me that the model is terrible. Believe me, this took us 3 meetings within the grade group to for the whole grade group to come together. And then we finally were able to write the concept paper. It's in JCB. But this is by far one of the more interesting developments in grade, where normally you make your inference and then you use inconsistency to see how much doubt you have in that inference. But now inconsistency is acting in 2 spots. First, it informs your inference, then it informs your certainty.
So the way to say here is consistently unsatisfactory.
Yes.
But that one is unsatisfactory. And so
Consistent, but that one you can fix.
but it's also consistent.
Yes, exactly.
And how do you add that? That it was homogeneous?
Yeah.
How do you add that other part?
Oh, that's just implications for future research, right? So here, I need to go and develop a whole new model. I have high certainty that I need to go and develop a whole new model. I have high certainty here that I can fix this model by recalculation. Yeah. So this is, somebody asked about subgroups. And so this was the Ebel study. We recreated the meta-analysis. And so this, our inference here was unsatisfactory model performance. And they didn't have any subgroups that could explain their heterogeneity. So we had some doubt, because in some instances, the model is performing. So if I make the inference that the model is unsatisfactory, I have doubts about that inference of unsatisfactory model performance, because in some cases, it seems to be satisfactory model performance. But then we did this subgroup that we thought about post-priority, which was to stratify the studies based on their overall risk, where we had the studies that looked at the patients who were between 5 to 10% risk, the less than 5% cohorts, and the over 10% cohorts. This is the overall risk of pneumonia in the cohorts. You can see for the intermediate groups of 5 to 10%, you would make the inference that the model performance is satisfactory. Maybe you wouldn't rate down for inconsistency, again, depending on where your margin of error is. Here, they're consistently showing you that the expected ratio was greater than the expected was greater than the observed. So the model is overestimating in the low risk. And in the high risk, they're all on the right-hand side, so the model is underestimating in the higher risk. So somebody asked about the subgroup, and this is exactly the thought that we had, and we did the subgroup, and it explained some of the heterogeneity that we were observing.
It has to be calibrated for these different risks.
You would recalibrate here, not necessary to recalibrate. But again, it's satisfactory or unsatisfactory world, because observed to expected is a limited measure to be done. Yes. So just to conclude on this, there's now 4 new concepts or rather considerations that we have for grade in assessing certainty and calibration of prediction models. That first is we need to be super clear about what is the target of our certainty assessment, which in this case is satisfactory or unsatisfactory performance. We need to be super clear on how to define this. Unusual, in order to decide on whether it's satisfactory or unsatisfactory, we use inconsistency because we can't rely on the full estimate. So we look at the totality of the studies to decide whether it's satisfactory or unsatisfactory. And then we look at inconsistency to see if we have doubts about that inference that we just made. And then, depending on what we're observing, it has bearings for what we do in the future. Do we make a whole new model or can we fix the model if it is not performing satisfactorily? So, thank you. I've been talking for so long, I've been so patient. I'd be happy to answer any questions you have.
So let's have a break,
Of course.
20 minutes, and then come back to see the updates on prediction models. Right?
This was the update.
Ah, that was the-
Yeah,
so
sorry.
we finished.
Yes, for that.
Okay. Good. No questions? I have a question. Like we've seen, like everybody's using now prediction models. Making, not using, making new prediction models. Why can't people do this like by day and by day to see what to do? Because we see a lot of new studies on prediction models.
Yeah, so the question is, why are people not doing more validation studies and just keep doing new derivation of models? And that's a really good point. That's a really good question. In fact, in Prognosis, when we get new students who come and they want to do prognosis research study, they often come to us and say, oh, I want to build a new prediction model. And my first response is, why? Can you convince me that there is absolutely no model in our area, in our disease area? And if you can prove that, well, how do you prove that? First, do a systematic review of all the prediction models that are out there. If you find that there is none, then sure, let's try to develop them. But by and large, we sometimes have prediction models that we identify from the systematic reviews. And what we find is that they're not validated enough in different contexts. So then the better question for the student to try to handle is take the model and try to validate it. That would be a much better use of resources than to keep making new models and have every single model. You know, in transplant, we have this problem in cardiac transplantation. We did a systematic review of the prediction models. There's tons. Not a single one is being used in clinical practice. Two reasons for it. Sometimes things in transplant aren't based on assessment of risk. So that's a problem with how we're doing transplantation. The management of patients, it could be better informed. Like, what would you do in a high-risk patient? What would you do in a low-risk patient? We don't think about that. We sometimes treat symptoms rather than risk. That's one reason that maybe a model doesn't get adopted. But the other reason could be that people just don't trust the models because they kept developing them, never validating them. So can I trust it? Am I now going to start suddenly changing my management when there's a model with somewhat modest performance that I can't have any reliability on? So better sense of resource. Once we did that systematic review, now we're dedicating resources to try to see if we can take those models and validate it in cohorts that we have access to. The other, I should mention this. This is a new, recent, interesting thought that we're having. Clinical context from clinical context has bearings on how people interact with prediction models. People love CHA2DS2-VASc for predicting the risk of stroke. People use it, the guidelines use it to make recommendations. If your CHA2DS2-VASc is 0, you don't need anticoagulants. If it's 2 or higher, recommend anticoagulants. If it's 1, shared decision making, depending on whether the patient is bleeding averse or stroke averse. Why do people love CHA2DS2-VASc? And when you look at the performance of CHA2DS2-VASc, it's not impressive, right? The C statistic is like 0.62. Not just that, but stroke is so unpredictable. Stroke is a very unpredictable event. Compare that to heart failure. In heart failure, we have models that are pretty impressive. Performance of discriminatory performance 0.78, We have good calibration on these models, but despite that, physicians, and they're simple too. There's a calculator, you can go, you put in your patient information, you get the estimate. We don't use them. The reason is because physician intuition is just as good as the model. You follow your patient for a long time. You follow a patient long enough, you know who's a really sick heart failure patient, you know who's not so sick heart failure patient. And so physician intuition is just as good as the model. And the physicians, that's one of the reasons we believe they don't love the models as compared to a situation where Chaz Vasquez worst performance in the models that we have in heart failure, but stroke is so unpredictable that if you have something that can help you with standardized practice, people aren't thinking.
Oscar has another question.
It's more a commentary. I agree that it's so better to calibrate, to validate a model than to create a new one. The sample size is a good reason. For developing a new model, it's necessary less 15 to 20 events for any variable that we are considering. So normally it in low prevalence events is low incidence events is a big sample size. For validating a model that exists, it's suggested that you only need 100 events, and that's taken from Provost document. I read it recently, and I think it's a good way not just to use better your resources, but to achieve a final result when you're students. So for me, it's a better idea to validate studies, and in fact, we are doing it a lot.
Yes, Oscar, I agree. And again, that initial systematic review is so informative to the decision and the direction that we take. If we do our systematic review and find there are models, and we find from our PROBAS assessment that we don't trust these models because their development was flawed, then of course, I would turn to my student and say, yes, you've convinced me, we need to dedicate resources to developing a better model, and then make sure that we convince the community to then take this model and run with it, validate it, not just stop at validation, but take it to an RCT where we move away from the surrogacy of the performance of the models being a surrogate for patient-reported outcomes. One of the first points that we made in this talk. I would also like to say, for the validation of models, sample size is also important. There's been simulation studies that have shown you need at least 100 to 200 events to be able to, with high certainty and confidence, see the performance of statistics that you're looking at. And this was based on simulation studies. So what they did, they had a massive population in which they looked at the performance of the model. So they had a very, very good sense of the truth. I'm talking like thousands of events, right? This was done in Europe, I think. And then what they did was they took that massive sample size and they divided it into smaller sample size. They sampled from that bigger study, and in each sample, they had different varying sample sizes. And they noticed that until you get to 100 to 200 events, the performance statistics that you estimate about the model is completely off from the underlying truth that you knew from the big population, right? So this was a way for them to determine the sample size that you need for adequately being able to do validation studies. Not a lot of people talk about it because a lot of people just stop at derivation, internal validation, but
Okay, thank you very much. Anybody else? Have coffee right now?
thanks everybody. It was great.
I can share the. Lily, para la clase.